And like I said, we'll only do like 15 minutes of this. And then we'll continue this later. It's recording. And let's create a new. So we're going to go back to block ciphers, right? So just think about that part. So let's think really about the command in OpenSSL, kind of to illustrate. And we've talked about how we have AES, and we've talked about how there's basically the mode of operations, CBC, right? So we've talked about this chaining. Now we're going to talk about these. We will only go into the details actually of DES. So if you remember, as far as block ciphers in the slides, we said that there are two very, there's many implementations, but two main frameworks frameworks or algorithms, which are DES, the data encryption standard, and AES, which is the advanced encryption standard. Okay. As far as DES has been broken. As far as I checked this today, as far as is known, AES has not been broken yet. Okay, as far as it's known. Okay. So, and it's, a lot of the, internet relies on that because OpenSSL uses symmetric encryption for part of its encryption. All right, so let's formally go back to block ciphers and provide a definition and then start building from there to leading up to the DES algorithm itself. Okay. So what are block ciphers basically? This could be a question on the exam, like how do you define a block cipher? Think about it, right? And you don't have, and I don't mean what is DES or AES, I just mean a block cipher itself. Like what would be the definition, a simple definition of a block cipher? Because at the end of the day, what do we know? We know that we usually have inputs, and then what do we have? Some kind of a function, would you agree? And then what do we have on the other end? An output. That's really what we're doing, right? So it's some kind of a function. It's got an input and an output. Usually the input is some block of zeros and ones, and the output is a block of zeros and ones. But there's got to be two conditions that are met, correct? One is in encryption and decryption, you have to be able to go forwards and backwards, right? So you have to be able to encrypt and decrypt, so the reverse effect. And then the other thing that has to be there, obviously, because we're encrypting is what? It's got to be secure, right? So we got to have security. So that's the security. Because that's what we're trying to achieve. So really, that's basically it. As far as the definition of encryption, sit down, people tired. All right, so as far as this, when we're defining, so if you ask yourself, so what are block ciphers? What are block ciphers? Right, as a question, then you can define this basically roughly as given an input through a function, and you get an output that meets the conditions of going forwards and backwards. So forward and backwards. And obviously that it provides security, whatever security it is that you want. Usually here, confidentiality. But it doesn't have to be that. It could also be what? Authentication or some other principle, okay? So that's the idea. So specifically now, we can drill down even further and think of a block cipher. So let's say block ciphers over here. Right, and we can say that the key idea, another way of writing it, this is usually how it's written actually, to define this, the key idea is that you have a function. The idea is a function that maps. Oops. A function that maps bits to bits. Right, that's basically it. So in this case, you do articulate that is n bits to n bits. Okay, so to specify the size of it, so the input and the output. Okay, so we then have block of n bits and a block of n bits. Okay, and then you're going to have encryption and decryption, right? And a key, basically. Okay, so if you remember, that is the block cipher. Okay. So these are the algorithms, of course, encryption and decryption. Now we have, there was DES historically. Then there was triple DES. And that was just basically, they said, okay, DES has been broken. We know it takes this long for them to break it. I think it was like a dictionary type of an attack. And so it was taking this long to break. So what was the simple solution? Let's just make it longer. So they did triple DES, which was literally running DES 3 times on the same message, right? So you would basically lengthen. And I think this was a temporary thing until AES came along, which AES was supposed to be more complex, but also needed to be faster than DES because it couldn't be super slow, because if efficiency is really important, right? Otherwise, let's say, like the example I always give you is you'd get bored, you get bored waiting 20 minutes for your movie to download, right? So you don't want that. Okay, so, and we saw in the slides that AES has bigger blocks, bigger keys, and so on, right? So that was established. All right, so now we're going to start. This is probably the last thing we'll do today. The idea of what is called the round key, and we'll kind of stop there, and then we'll pick up with DES the next time we meet. Okay, so let's go ahead and just do this. Let's talk about block ciphers. Block ciphers use something called round keys. Okay, so you get a key, you start with that, and then you expand the key actually into a whole bunch of keys from that key, similar to the idea of the stream cipher, where you have one key and a pseudo-random generator to constantly generate bytes. You can do the same idea, but now you have one key and you make more keys out of that key through some function, as you might imagine. So step one, get a key. Okay, step two, you're going to expand the key. You're going to expand the key into a sequence of keys called round keys. Okay, so you're going to expand the key into a sequence of keys called round keys. Round keys. Okay, and then step three. Step three, the message is encrypted using these keys, basically. All right, and that's the normal procedure for this. So use all keys. So we'll do a diagram that will be the last diagram for today and kind of illustrates the idea. So we're going to have, and I'm out of this place. Let me erase this part. Right, so the idea is actually, and if you think about it, it's almost like you're just deliberately adding more complexity every time. So once this is like the first time that you'll see this. So before it was like very elegant, you do like move things and you do an XOR operation. But now you're deliberately like, okay, let's, instead of 1 key, let's have 16 keys. And then once we get into des, you're going to see, okay, let's just jumble this in some way and jumble it more. And so you're just adding more changes to the original block. So you take 1 key of a specific size, it'll run through a function, a round sequence function, and this just generates keys of the same size. So this would be K1 now, this would be K2, this would be K3, all the way to Kn. Okay, and now what do you have on this side? This is just for 1 block. Okay, so this is just for 1 block. And we won't implement this in Python, so we're not going to go this far. But let's think that this is of 128 bytes, so that these are also 128 bytes. So what do? What's the operation we've been doing constantly? We XOR, right? You XOR, and the output of this, which is of the same size, gets XORed with the next one. And that's it. I mean, that's what the round keys part is. But whenever you hear that in the algorithm, that's what's happening. Instead of just doing it once, block to key, imagine there's like this area where the plain text goes in, the key goes in, it gets expanded into a whole bunch of keys, and then you just go through all of them. Okay? And the idea is, although those are coming from a deterministic algorithm, at least you have more, and it's harder to break. Does that make sense, guys? Yeah, please, go ahead.
So every single block has to go through all of them.
Yes. Yeah, let me finish it. So that's a good question. So this M is the plane, right? So I'm not putting a number on it. Okay. And then this would be the key 1 with M. They're both the same size, 128, 128, 128, 128, right? So you can control that. And then here you get now, let's call it M1. Because I don't want to confuse it. It's technically C1, but I don't want to confuse it from the fact that the cipher is usually so let's just call it M1. But you know that if this is a key, this is, in theory, you can't make this out anymore. Okay. And then this goes into the next one, which gets XORed. And then like that, K3, and this is M2, the output of this one. So you take K1 and M, and it produces M1, the XORing operation. This is a key expanded from this original key, which should be as random as possible. And then M1 XORed with K2 produces M2. And then here, this would be M3, right? And let's just say it goes all the way over here to the final XOR operation. And then this one is what I'm going to say is the cipher, just to kind of, the final one. Now you can imagine this is easily, just a box that says round keys that takes in a key as input and a plane, and it produces a C. What happens inside, it's really, you can control through the code. And this should be 128 bits. Got it, guys? All right, so this is kind of, we haven't gotten to des yet, but this is kind of the stepping stone. And then next time, I'll decide if I do some coding on the lab or if you just continue the lecture, okay? But there won't be any homework this Thursday, as I said, because I want you to study for the exam though. All right, which is a week from today. Please do not forget that. It'll cover basically until what we cover Thursday. Okay? All right, so I'll stop now and we're done for today. See you guys on Thursday.